Okay, so what we're going to be doing now is talking about magnetic circuits. So the first thing we're going to do is go back and look at electric circuits. So with electric circuits, the basic equation that we have constant is the voltage. So we had an electric field dot dl, and so we found out that that was equal to the voltage. Okay, and so we are going to get that the voltage is called EMF, electromotive force. And this is very similar to what we just did, which is H dot dl, which we said was equal to NI. That's Ampere's law. So then what we're going to do is NI is called MMF, which is magnetomotive force. Okay, because of those equivalents. So now what we see here is we have an equivalence between Ni and voltage. And the equivalence just means that it has the same mathematical relationship. Since it has the same mathematical relationship, the concepts that we used for voltage, we could also use for magnetics because we understand the circuit stuff better than magnetics. So we find out similar math. And if the math is similar, then I could use similar techniques. Okay, so let's keep going on our electric circuits. So in an electric circuit, we use the voltage to produce a current. Well, how do we get that to produce the current? Well, it depends on the material. And we use the concept called called resistance. So the resistance is equal to the length divided by the conductivity of the material divided by the area. So what we see is if my resistor is longer, it has more resistance. And if my resistor has more area, it has less resistance. Okay, and then depending on the actual material properties, which is the conductivity. And so we have this resistance relationship, okay? So what is the equivalence over into the magnetics, okay? So in magnetics, we have the magnetics produces flux, which we called capital Phi. So what we had is we had flux is equal to the flux density divided times the area, which we found out was equal to mu times Ni times A over the length. And the length would be the length of the solenoid or the length around the toroid. Okay, so if we reorder this, we want the Ni, which was our magnetomotive force, and then we multiply that times mu area over L, which is equal to Ni divided by L over mu area. Oh, well, if I come back up to my circuit equivalent, we had that my current is equal to the voltage divided by the resistance, which is the voltage divided by L over sigma times the area. Oh, well, look at that. So we see that this piece right here and this piece right here look again very similar. Okay, and that's this concept of equivalence. So we're going to take this term right here and we are going to call it reluctance. And it uses a curly R, sorry, and it's L over mu area. And we can see that it's driven by this Ni. So the Ni is similar to my voltage. And then this is my reluctance, which means that now, and this was my flux, see that my current right here and my flux are equivalent. Just to finish all of this off, we can see that I have an equivalence between these two right here. Okay, so we have all these equivalents. Okay, so this got a little bit messy, so let's write down all of our equivalents now. Okay, so we're going to put our magnetics over here and our electric over here. Okay, so let's start with our our forcing thing, which is our potential. So over here, we had an I, and over here I had voltage. Okay, we found out that the flux is equivalent to my electrical current. We have my B, which is equal to my J, which is my current density, I over A, and this is basically the flux density. Okay, we can keep going, and we have our reluctance and our resistance. And in the reluctance term, we had a mu over here and a sigma. So the sigma, which is my conductivity, is what kind of determines the material property that gets electrons or current flowing. And mu is the amount of magnetic flux that I do relative to my magnetic field, which is created by my magnetomotive force, which is my Ni. Okay, so we have all of these equivalents now. So you can see that anything that I used, I can just make these equivalents over here. And now what I can do is I can use all of my knowledge that I've developed for circuits and apply it over to magnetics, which gives me a lot of power to do more complex structures. In electrical circuits, I can do much more complicated circuits using these concepts than I could using the straight physics. And so then I can do the same thing for the magnetics. Okay, let's do a quick example and show how this works. Okay, so let's look at our solenoid. So if I have a solenoid and I have some wire wrapped around here, and I put a current source in here of current I. Okay, so we're going to do our magnetic circuit. Okay, so we're going to start with our magnetomotive force, which is basically our magnetic voltage source. Okay, and then I am going to come over here and do a reluctance. And my reluctance R has a value of L over sigma A. Well, let's go and plug in these numbers from our solenoid. So our L is 2 pi big R, and we had our sigma, and this was our pi little r squared, which is our cross-sectional area. So now we're using our circuits, and so now we're going to say our flux, because we see right up here that our flux is equivalent to our current. So our flux is going to be equal to Ni divided by our reluctance, which is equal to Ni divided by 2 pi r over sigma pi little r squared. Okay, which is equal to Ni, oops, not sigma, mu, because these are magnetic circuits, not electric circuits. And then this is going to be mu r squared over 2r. Okay, and then we can, once I have my flux, I can calculate whatever I want. I can do B is equal to the flux over the area. I can go that my inductance is equal to lambda over I, which is equal to N times flux over I, which is equal to N squared mu r squared over 2 big R. And you can see that we solved all of our solenoid type problems using this same basic idea. So I didn't have to go back to all the physics. I could use my concepts of circuits to do this. And so this is going to give me a lot more flexibility in order to do more complicated structures. Okay. Just as an example, we can start doing transformers with different type of magnetic structures using these concepts of circuits. So it's really powerful using these equivalents because then all of the knowledge we gain for electrical, we can apply to magnetics. And we're able to do this because the basic math runs the same. There aren't really magnetic circuits, but it's just a easy way in order for us to use the similar math to solve everything. And then that is called magnetic circuits.